Imagine a small device that can store electrical energy, kind of like a tiny battery. But unlike a battery, which stores energy chemically, a capacitor stores energy in an electric field. This allows it to charge and discharge much more rapidly. That's essentially what a capacitor is. It's a fundamental component in electronics, playing a crucial role in various applications. Capacitors come in many shapes and sizes, each designed for specific functions. Some are tiny, used in delicate circuits, while others are large, used in power systems. They are found on almost every circuit board, from the simplest gadgets to the most complex machines. A capacitor can hold a charge of electricity and release it when needed. This ability makes it indispensable in electronic circuits. They are used in many electronic circuits, from simple to complex. For instance, they help in timing applications, where precise intervals are crucial. Capacitors are found in almost every electronic device we use daily. Your smartphone, television, and computer all have capacitors working behind the scenes. They help in stabilizing power supplies, ensuring that your devices run smoothly without interruptions. Capacitors are essential for things like smoothing out voltage fluctuations and filtering signals. This makes them vital in audio and radio frequency applications. Unlike batteries, capacitors charge and discharge much faster. This rapid response time is crucial in applications where quick energy bursts are needed. This makes them suitable for tasks that require quick bursts of energy, such as in camera flashes or defibrillators. They are also more durable than batteries, and can handle a higher number of charge and discharge cycles. This longevity makes them ideal for industrial applications. In essence, capacitors are like tiny energy reservoirs that play a crucial role in making our electronic devices function properly. They ensure that our gadgets are reliable, efficient, and ready to perform at a moment's notice. A capacitor is constructed with two conductive plates separated by an insulator. These plates are typically made of metal, such as aluminum or tantalum, which are excellent conductors of electricity. The insulator, known as the dielectric, can be made from various materials like ceramic, plastic, or even air. This insulator is called a dielectric. The dielectric material is crucial because it increases the capacitor's ability to store electrical energy by reducing the electric field between the plates. The plates are made of materials that can hold an electrical charge. When a voltage is applied, electrons accumulate on one plate, creating a negative charge, while the other plate loses electrons, creating a positive charge. The dielectric prevents the plates from touching each other. This separation is essential to maintain the electric field and store energy efficiently. When you apply a voltage across a capacitor, it starts to store energy. This energy is stored in the electric field created between the two plates. This happens because an electric field builds up between the two plates. The strength of this field depends on the amount of voltage applied and the properties of the dielectric material. The dielectric material plays a crucial role here as it can store energy within its structure. Different dielectric materials have different abilities to store energy, which affects the overall performance of the capacitor. The amount of energy a capacitor can store depends on its capacitance. Capacitance is a measure of how much charge a capacitor can hold at a given voltage. Capacitance is measured in farads. 1 farad is a large unit, so capacitors are often rated in microfarads, UF, or picofarads, PF. A higher capacitance means the capacitor can store more electrical energy. This is useful in applications where large amounts of energy storage are required, such as in power supplies or audio equipment. The choice of dielectric material and the distance between the plates are important factors that determine the capacitance of a capacitor. By selecting the right materials and design, engineers can create capacitors that meet specific needs for various electronic devices. Think of a capacitor like a water tank, a simple yet powerful analogy that helps us understand its function. Imagine this water tank has a rubber membrane separating it into two compartments. This membrane is crucial for the tank's operation. When you connect a pump to one side of the tank, it pushes water into that compartment, increasing the water level on that side. This process is similar to applying voltage to a capacitor, where the voltage acts like the pump. As the water level rises on one side, it pushes against the membrane, storing potential energy in the form of pressure. The membrane in the water tank acts like the dielectric in a capacitor, a material that separates the two plates. It prevents the water from flowing back, maintaining the pressure difference between the two compartments. Similarly, when you apply voltage to a capacitor, It stores electrical potential energy in the electric field between the plates, just like the water tank stores pressure. The dielectric material prevents the charge from flowing directly between the plates, ensuring the energy is stored effectively. The higher the voltage you apply, the more charge builds up on the plates, increasing the stored energy. This means the capacitor can store more energy, similar to how a water tank can store more pressure with more water. Just like increasing the water pressure would store more energy in the tank, increasing the voltage stores more energy in the capacitor. This analogy helps us visualize how capacitors work in a tangible way. Now imagine opening a valve on the water tank. The water rushes out, releasing the stored energy. Similarly, a capacitor discharges when you provide a path for the stored charge to flow. When you connect a load, such as a light bulb, across a charged capacitor, the stored charge flows through the circuit. This flow of charge is what we call electric current. As the charge flows out, the voltage across the capacitor decreases. The capacitor continues to discharge until all the stored energy is depleted, much like the water tank emptying out. The rate at which a capacitor discharges depends on the resistance of the circuit. A higher resistance will result in a slower discharge. Section 5. Different capacitors, different jobs. Just like there are different types of batteries for different purposes, there are also various types of capacitors. Each type has unique characteristics and applications. Ceramic capacitors are small and stable. They are commonly used in high-frequency circuits. Electrolytic capacitors can store a larger amount of energy. They are often used in power supplies. Variable capacitors allow you to adjust the capacitance. They are used in radio tuning circuits. The choice of capacitor depends on factors like the required capacitance, voltage rating, and the operating frequency of the circuit. Section 6. Capacitors in action, real-world examples. Capacitors are everywhere in our electronic devices. They play crucial roles in various functions, making them indispensable components. Smoothing voltage. In power supplies, capacitors help smooth out voltage fluctuations, providing a stable direct current output. Filtering signals. Capacitors can block direct current signals while allowing alternating current signals to pass through, making them essential for signal filtering. Timing circuits. Capacitors can be used in conjunction with resistors to create time delays in circuits, like in a simple timer. Energy storage. In some applications, capacitors can act as temporary energy storage devices, providing backup power or quick bursts of energy. These are just a few examples of the countless applications of capacitors in electronics. Section 7. Choosing the right capacitor, key considerations. When selecting a capacitor for a particular application, several factors must be considered to ensure optimal performance. Capacitance value. This is the most crucial parameter. Choose a capacitor with the appropriate capacitance for your circuit. Voltage rating. This indicates the maximum voltage the capacitor can safely handle. Always choose a capacitor with a voltage rating higher than the circuit's operating voltage. Tolerance capacitors have a tolerance value that indicates the acceptable range of capacitance. Choose a tolerance level that meets the requirements of your circuit. Type and size. Consider the type of capacitor suitable for your application, and choose a size that fits your circuit board. By carefully considering these factors, you can select the right capacitor for your project. Section 8. Troubleshooting capacitors, common problems. Like any electronic component, capacitors can sometimes fail. Understanding common capacitor problems can help you troubleshoot issues in your circuits. Short circuit. This happens when the dielectric material breaks down, allowing current to flow freely between the plates. Open circuit. An open circuit occurs when the capacitor fails to conduct any current at all. This can be due to a broken connection or a faulty dielectric. Leaking. Some capacitors may experience leakage current where a small amount of current flows through the dielectric even when it should be blocking it. If you suspect a capacitor is faulty, you can use a multimeter to test its capacitance, resistance, and voltage. Section 9. The future of capacitors, innovations and advancements. The field of capacitor technology is constantly evolving. Researchers are continuously working on developing new materials and designs to improve their performance and energy storage capabilities. Supercapacitors, also known as ultracapacitors, these devices can store significantly more energy than traditional capacitors. Graphene capacitors. Using graphene as a dielectric material shows promise for creating capacitors with higher energy density and faster charging times. Solid-state capacitors. These capacitors use solid electrolytes instead of liquid or gel electrolytes, offering advantages such as longer lifespan and higher reliability. These advancements in capacitor technology pave the way for exciting new applications in areas like electric vehicles, renewable energy, and portable electronics.